Dragos, good morning.
Good morning.
How are you?
I'm good, thank you.
Okay.
Thank you.
Thank you for coming out and being on the show today.
It's my pleasure.
I wonder if we might start just by asking you to tell me a little bit about Earth observational science and what that's involved and what happens there.
Earth observation simply means exactly what the name is, observing the Earth. So basically it's a big field that started way back in the 50s and 60s when the US started using airplanes for observing various activities on Earth. And then in the 70s, they started building the first satellites with Landsat 1 and 2 in the 1970s. And then they've been building satellites ever since, better and better since, for monitoring activities on Earth. So Earth observation simply means observing activities on Earth from above. And nowadays it can be from drones at a few hundred meters. It can be helicopter or aircraft a few thousand meters. It can be satellites. They usually fly about 700 kilometers above Earth. So, and looking down, they take pictures with different sensors of the surface of the Earth. So that is Earth observation.
And what is that information generally used for? Like, what are they observing and looking at?
Anything you can think of. Obviously, first of all, the first uses were military when in the early days when they started, and that use is still present today. So the biggest user of Earth observation, the biggest users of satellite imagery is obviously the defense part. But on the government, civilian, you can see basically Earth observation gives you a snapshot of the Earth in time at a particular place. So that means you can look at the environment, you can look at the expand of forests, you can look at the state of agriculture, you can look at the quality of water, you can look at the development of cities. You can basically whatever you can see from space, it can become an application in itself.
And the information that's captured, is it centralized into databases that are accessible to the public, or is it private?
There's both. So what you have is, and I'm going to talk nowadays because there's a wealth of data coming from satellite, and you have two main programs that bring data in an open fashion. You have the US Landsat program, and they've been delivering free data since 1972. It wasn't initially free, but eventually they opened it up, so now it's free. So since 1970s up until today, all the Landsat archive is fully open. So that's the US part of it. And the European Copernicus program, all the images coming from the Sentinel satellites, they are freely open to the whole world. And I think this is an amazing thing for countries that do not have capability to launch, because they can tap into the same information as Europe nowadays. So think, for example, to be able to use a satellite image for a particular purpose. So let's say you want to monitor the state of the environment in a country, right? You have to design a satellite, you have to build it, you have to put it on a rocket, you have to launch it, you have to fly it, you have to take pictures, you have to download the data, you have to know how to interpret, and then you have your final output. But all this is freely given by Europe. So whether you are in a Pacific island or you are in a country that maybe they don't have capability to build.
Even New Zealand, perhaps. I don't know if we have satellites for that. I don't know if we have that capability.
We don't have.
Yeah.
So all of this is simply offered freely by Europe. So all you have to do is know about it, reach out to the data, and having the knowledge and do something with it.
I see. And so that's I'm guessing that's pictures, that's visual images taken. What other sorts of scanning, or do they do from satellites and drones?
So from satellites, mostly there are two types of sensors. You have the multispectral, which simply means photography, but not only in the natural color. So a natural color simply means what a phone camera would take. What you see with your eyes is what the sensor picks up. However, satellites can also see in the infrared, can see in the thermal. So a phone usually has 3 bands, red, green, and blue. Satellites have 8. So you can have yellow, you can have near infrared, you can have short infrared, you can have thermal, and so on. So you pick information across a wider spectrum. And those are the passive sensors that can only work when there's no clouds.
Mm-hmm.
If you have clouds, optical and the passive sensors...
You get lots of grey pictures.
Exactly. So you cannot see through them. However, you also have radar satellites. They are called synthetic aperture radar, and they can see through clouds. So while the optical ones, they capture just as a picture reflected information, the SAR, the radar satellites, they send pulses to the Earth, and they record back the scatter.
So do the radar ones, which can see through the clouds, are they capable of doing like terrain mapping? Are they getting 3D information of the geography and the terrain, like the shape of the ground with the radar?
You can do that, yes.
Yeah.
So an interesting analogy is in the optical spectral images, you see, so the sensor sees what the sensor sees. So you see what you see. In the radar domain, you see what you hear, which means you the reflected, the echoes of the Earth coming back to the sensor.
Yeah. Yeah. Okay.
Yeah.
So there's visual, the radar. Are there things like ground penetrating radar that can be done from these areas? Do you know? Is it something can you detect what's under the ground or in the water?
Yes, but so it's not a ground penetrating radar like the one that you have on the ground, like the machine that goes very deep is very different. However, you can use some satellites for example, archaeology. So there's been archaeological studies using satellites that you can see through a thin layer in the ground. Usually in places like Egypt,
you can see through the sand.
You can see through the sand up to a measure. So the structures that you are not capable of seeing while walking around, when you see them from space, they show up.
That's pretty amazing.
But not 100 meters deep. It's just under the surface, so you can see some patterns that are not natural, so then you can go and investigate more.
Those areas.
Yeah.
That's really cool. That's really interesting being able to do that sort of thing in Egypt, because I know there's still thought to be quite a lot of megalithic development under the sand, and some of it forgotten, people not knowing where it is.
Yeah, so it's possible. You detect some patterns, and then you go and you begin to dig.
So it becomes a tool to help you locate lost treasures in a way.
Oh yeah, and actually there's a book called Space Archaeology that's quite interesting. It's a lady who's been doing this for 30, 40 years maybe, using satellites and aerial photography, even dating back to the 1960s from the and she's using these images to detect archaeological sites either in Egypt, maybe South America, in the Amazon, and so on. So it's very interesting.
That's really interesting. Yeah, 'cause I've been wondering just what the range of activities are that
and you can also see through water. It doesn't really work in New Zealand because the waters are very rough. But if the waters are still and clear, there is a field called satellite-derived bathymetry that you can use satellites to actually map the seafloor and the column of water or whatever it's under the water up to a certain measure.
Wow.
Yeah.
That's pretty amazing stuff. So What is your background? How did you get into this area, and how do you know about this?
I was doing my studies in Romania, so I'm from Romania originally. I was studying electronics engineering, and for 4 years of university in Romania is 5 years. They combine kind of both bachelor and masters into one 5-year program.
Okay.
And I hated it. I didn't like it, and I spent 3.5 years, even 4 years, just pushing through.
Yeah.
But however, in the 4th year, I discovered the field called image processing, and it was perfectly for me at this intersection between art and science. I was always been on this fine line
edge.
between, on the edge, exactly. Like too much science becomes dry and dead.
Yeah.
Too much art becomes too fuzzy, and I don't like it, and too emotional.
Yeah.
But I always like this very narrow path of what is, in the middle.
The interest zone.
Yeah.
The zone of interest.
Yeah, so too much technology, like I didn't want to go into sensors, and that's too technical. And I didn't want to go into photography as an art because it's too
Too nebulous, not enough to hold on to,
Yeah.
and be certain about, I guess.
Yeah, so but when I discovered the field of image processing, basically the science of imagery, the science of colors, the science of light, how an image is formed, and how to interpret the data, and how to write algorithms, even data mining and for images, that was the sweet spot. So then I found I was offered the chance to do a PhD in Germany. I remember I finished my university, and a professor from the German Space Center came, and he asked me, "Do you want to do a PhD?" And I remember I thought, I have no idea what a PhD is, but I just said yes.
Good.
So, and then he introduced me to the field of satellite imagery, and it was fascinating. So it was like the next level up about photography and sensors, but from space. And not only in RGB, red, green, blue, but in actually across a wide spectrum and many applications. It was fascinating. So that's how I started. I did about almost 7 years at the Romanian Space Agency as a researcher. And it was all about the field of Earth observations and using satellites from space.
What were you doing? Like, what were you working on in terms of taking images and then trying to derive what or understand what from those images?
There's been so many. There's been so many, because basically anything that can happen on Earth, when a satellite flies over, you can see. So I was involved in, for example, disaster management. We had floods in Romania, so we used satellites to task and to see the extent of the floods. And we've done the same in New Zealand recently with the satellites. There were many applications in the sense of mapping the land cover, to seeing the land cover of countries in Europe at the time.
Being able to say, we're looking at the countryside, and on this date we've got 18,000 square kilometres of what appears to be old growth forest, and 20,000 kilometres of what appears to be new pine commercial forest, and agriculture ploughed fields 40,000 kilometres, and then looking at that over time. So did some of your studies span years, or are they still ongoing? Is it something that just every year they're just accumulating more data? Because I imagine what's interesting is that delta, the change over time, being able to detect that. Is that what some of your research was into? Was like, how do I take this photo and then calculate the delta between them so that we can see how things are changing? Old growth is reducing, commercial forests are expanding, that type of thing.
So I wasn't doing particular. You can use Earth observation for this. So a great purpose in using satellites is exactly what you say. You can look back in time, and you can start in the 70s, and you can see how your country or how your particular area has changed for the last 50 years.
Yeah.
And depending on, you can look at the change of the country, or you can look at the change of a building or a development. So you can, depending how quickly you want to observe the changes.
So you can detect growth of a city and do city planning
Exactly,
and that
yes.
type of thing.
Yeah, I just finished delivering some trainings in South America and in Africa, and it's amazing to see how, for example, in some places in Africa, 30-40 years ago, there was no city. It was a tiny village or a small city, and now it has become a metropolis, and you can see all that.
And you can, I imagine that also, if you're looking at a city, you can, I imagine you should be able to use this for urban planning. You go and look down on all of the cities and start to maybe combine that with like Google traffic data to go, okay, this design, this sort of grid of streets keeps on giving us congestion in these areas. What could we do to model a city if we're going to build, which is different, I know, more roundabouts or whatever it might be.
Yeah.
But that sort of information.
Like, for example, we do it in Auckland as well. However, in Auckland is slightly different because the quality of the data that we require is so high that satellites at the moment cannot provide that kind of precision and accuracy. So we use we employ aircraft for this purpose.
Yeah.
Yeah.
Is AI starting to move into the field to be able to, well, maybe even address that issue where you don't have the precision from the photographs you've got, you don't have the precision, but could you take AI to sharpen and upscale and get more out of those images?
Yes and no, and I'll tell you why. So when it comes to the field of Earth observation, because I've worked in research, I've also been in the commercial private space, and I've also been in the government space. So I've been kind of on every side of the equation. In the research field, in the academia, people take satellite images and they say you can do this, you can do that, and they show it on a very tiny scale. But realistically, the crossover from research, from papers, from journals into the real world it doesn't really work in practice as it's done in theory.
Yeah.
So I'm really careful when it comes to, can you do this? Well, in theory, you could do some things, but not to the level that sometimes is being promoted.
Yeah.
And for example, you can take satellite images that have a resolution of, let's say, 30 centimeters. And through various methods, you can enhance it to 15 centimeters. You can sharpen it. You can make it better. However, the quality itself, the resolution of the information itself, it's still 30 centimeters. So you cannot add information to what's not there. It's like,
unless you guess.
You guess it, you can maybe predict it, but still it's not real.
Yeah.
So it depends on what exactly is the question.
Yeah.
Because if you want to make it into a visual product for some purposes, yes. But if you really need information,
the data of what's really there.
It's not there.
What is it? What sort of things is it that requires you to use photographs taken from planes rather than satellites to give you that less than 30 centimeter definition?
So think about it like this. A satellite flies at 800 kilometers plus or minus, but roughly 800 kilometers above Earth. And you have a snapshot of, let's say, Auckland, taken from 800 kilometers. So the quality is absolutely extraordinary.
So your one photograph covers an area of how much?
A few tens of square kilometers.
Uh-huh.
So from 800 kilometers, this thing flies at tremendous speeds and takes a snapshot. And you can see objects that are 20, 30 centimeters big.
Yeah, it's amazing.
So you can see cars, you can see all sorts of things. But the precision, the accuracy, so it doesn't necessarily mean that because the speed is so high, sometimes it can be slightly shifted from the actual location on the ground.
Blurred slightly, or like parallax, you're looking at it from an angle?
Not
No?
blurred, but the spatial positioning might be slightly shifted.
Okay.
And an aircraft flies at 2,000 meters, so 2 kilometers. So 2 kilometers compared to 800 kilometers. And obviously it's much slower. So an aircraft can take pictures with a resolution of 3 centimeters. Usually we do about 7 centimeters.
Mm.
So you can see the smallest object you can see is about 3 to 7 centimeters from aircraft.
A tennis ball. You could identify a tennis ball on the ground.
So that's the difference.
Yeah.
And also because they fly lower and because the resolution is much higher, the spatial accuracy is also much higher, which means that your house from an aircraft on a map will be exactly where the house is, but from the satellite, it might be slightly off.
Okay.
So it depends what precision do you require of the data. And
with the work that you're doing, what things are you doing where you require that really fine 3 to 7 centimeters? Like, what are the client or the business looking for in that case?
What you said, urban planning, urban mapping, because when you do the mapping of, properties, and they have to be very precise because otherwise they fall into the neighbor's land, so it's not.
That makes sense.
Yeah.
So being able to actually measure, look down and see fence lines and then calculate the area of a property.
Exactly.
You want to be accurate on that.
So if, for example, if you're the defense force looking at activities in Ukraine, it doesn't matter if the army is here or slightly to the left with 50 centimeters or 50 meters,
Yeah.
But when it comes to your property, it matters because 50 meters,
50 centimeters,
it's the neighbor's house.
Yeah.
So it depends on the precision of what you're trying to map on the ground.
That makes sense. That makes sense.
Another example is is what's called interferometric radar. So if you have 2 satellites that record radar information, you can actually see the subsidence of buildings. You can see the subsidence of the terrain. I remember having studies back in Romania where they could monitor and measure how like a big palace building or a big construction is subsiding on, and you can actually measure a few millimeters.
Wow.
Of movement up and down. They've done the same in Auckland last year. There was a study done using satellites where you can see how buildings and neighborhoods and even the harbor bridge goes up or down with and even slight changes in millimeters you can see from satellites. So
for something like that, is that Auckland Council or is that the New Zealand government that's doing that research? In Auckland, like to find out, you said they scanned to see how the bridge had moved up and down. Is that something done by a private company or by a Auckland Council? Do they want to get that information?
So the local government is the one that's sponsoring, but there was a company from Europe doing the work.
And so in that case, the local government, they're going to a satellite company, European satellite company, and requesting that you give us data here, over New Zealand. And is that something that satellite company would be doing anyhow? Like, are they just flying around and always having 2 radars scanning wherever they're going? Or would you be asking that satellite company can you please turn on 2 radars when you're over New Zealand this week and scan specifically for us?
Yeah, all of it. So, because of the European space program, So Europe has the Copernicus program. Part of the Copernicus program is they operate satellites, radar satellites, optical satellites, and these satellites are continuously capturing information, and that information is freely shared. And this is what the European Union is doing. Now, this enables a lot of small, medium, even big companies to take the data and to create services based on the data. So it's not a satellite provider, but it's a company. Usually, it's a data analytics company or that they take the data and they create a service based on it, and they sell the service.
Okay.
So this means that the European program enables private companies to develop new services, add new value, and grow the industry and provide those services all over the world. So in this case, the company itself from Europe, they do this on a client-by-client basis. So when the need arises, they take the data that's already available, or they task a commercial satellite and they capture the data for specifically this purpose, and they create the service, the outputs, and they sell it to the customer.
And that's expensive, I imagine, to be able to request that specific use of a satellite.
The cost has gone down a lot. So the good part nowadays is because you have two options. You have the free, fully open satellite data.
And is that the full range of data? Is that visual spectrum as well as infrared and radar?
Yes.
All of that's from Copernicus is available
Free.
Yes. To anyone. You or I could go and access that data if we wanted to?
Yes.
Wow.
Just search Copernicus Science Hub or on Google, and it's all there.
Okay.
So, however, Copernicus is medium resolution. So, for example, when the optical, it's about 10-meter resolution for the images. The commercial companies usually have much higher quality, much higher resolution. So if you can't afford to go fully commercial, you can use the open one. But if you require much more quality and resolution and accuracy, you need to go commercial, and there's a cost for that.
So is that a limitation of the Copernicus satellites? They can't give any greater resolution than that, or do they have higher resolution images, but they only release to the public a lower resolution version?
No, they have been designed. So the purpose for Copernicus is mostly environmental monitoring, climate change. So they have been designed for this purpose, and this purpose means that you have to look at wide regions.
10-meter resolution's fine for what they're doing.
For the environment is great.
Yeah.
So the purpose for which they've been developed is it's met. So, but the commercial companies, they mostly rely on defense customers, and for defense customers, you require much higher level of information.
So the satellites that do the mapping, are they? Let's say the Earth is here, for people who are just listening on Spotify or something. So you've got the Earth here. It's a sphere.
Yeah.
Are the satellites rotating around the Earth, or are they geosynchronous? Are they held in one spot and always looking down at the same spot?
No, they fly around.
They fly around.
Yeah.
Can you get geosynchronous ones? Like if you wanted to, could you put a satellite which would just sit above Auckland so that you could always be like getting real-time data from an area?
So there are those kind of satellites, but not for Earth observation. Because the thing is, in order to be able to do Earth observation, it has to be at a lower altitude. So the only way to be at a lower altitude is for the thing to fly at high speeds.
To keep it in the orbit, otherwise it'll drop down to Earth.
Exactly. So,
okay.
But if it's geosynchronous, so if you want it to stay in one place, basically they don't stay in one place. What happens is they have to spin in the same time with the Earth.
Yeah.
But for that to happen, they have to be a lot higher.
Ah,
So if they are so much higher, then the resolution will be extremely low. So it doesn't
right.
do good. Yeah.
So though that orbital where those satellites would sit at a higher level are more likely to be facing the other way then, looking out into space.
Like Hubble Space Telescope is one example.
Okay. Are they would they be using Lagrange points, those points around the Earth where you can pop something there and it will just stay there, or is that different again? The satellites being able to do that, because I've heard that there's around Earth and I think around the Moon, I think any of the planets, there are some points. I think there might be up to 5 of them called Lagrange points, where for whatever reason, if you drop a satellite in that spot, it will just stay there. It's held there. It's like, but like, yeah. So I wonder if that's what they're using there, or if it's just a higher level orbit around the Earth and they stay geosynchronous because of that.
Oh, this is how this simple way of understanding it really helped me a lot to understand how satellites actually stay into space.
Yeah.
You know, for example, if you take a tennis ball, and if you throw it with your hand, it will eventually fall after a specific distance and time. It will eventually fall because of gravity. Now, if you take a ball and you throw it with much greater force and much more speed, it will do the same, but at a different
it'll fall further away.
Yeah, so it will fall, but it will fall much further.
Yeah.
Now, when it comes to satellites, imagine if you could take a ball and throw it with such speed that it keeps falling but never really falls.
Yeah.
So it's so fast that it just constantly falls but never falls. Just keeps going and going and going.
So it's caught in a balance between gravity pulling it down and the speed. Centripetal force of the speed trying to send it out all the time.
Yeah. So if you send something fast enough that the gravity pulls it but it keeps going, that's how satellites stay into space.
So do they stay in space? How long will satellites stay in space? Do they eventually fall? Because I know you hear all the time of satellites re-entering the Earth, and someone saw something at night time and it was a satellite coming in. Will eventually that happen to all of these satellites? Because they don't have power packs, do they? They don't have any. Do they have a power supply to keep pushing them up a little bit?
Yeah.
Oh, they do.
So they have solar. So what happens usually? Satellites are designed for a specific lifespan, some of them for a few years, some of them for decades, and eventually the fuel runs out. And ideally, when the fuel runs out, they get decommissioned in a controlled way. So, when you have something out there flying when the fuel runs out, because the fuel basically is what keeps the thing going. There's 2 ways of getting rid of them. One way is to let them fall through the atmosphere of the Earth and they burn in the free fall, or you use the last bit of fuel to thrust them further into space and you chuck them
and just let them go.
So, but anything between can happen. If sometimes they can fail and you can't control them anymore, so they stay there, and it's called space debris, space junk. Sometimes if there's a collision, they can just disintegrate, and so one satellite, and usually the satellites are the size of a school bus.
Wow.
Yeah, so nowadays you have various sizes, but
that's huge. I always imagine satellites as being like the size of a bit bigger than a basketball, not the size of a bus.
No, so nowadays you have satellites from Planet, and they are kind of like, you can hold them in your hand, so they are small, and they are cheap, and they can fly hundreds of them in orbit, and when they when their life goes out, they just send new ones. But the big commercial ones, like Hubble Space Telescope, for example, like the Landsats, like the European ones, they are the size of a bus.
Yeah, wow.
Like Hubble Space Telescope is the size of a school bus. That's how big they are. And can you imagine and they fly at tremendous speeds, and one tiny particle hitting that can create millions of bits of pieces of space debris. So,
Yeah.
and those bits and pieces, when they continue flying, they actually endanger the other satellites still there. And the more we launch, I think there's thousands nowadays flying into space. Most of them you never hear about, but there's probably thousands of satellites going around the Earth.
Yeah.
And space debris is becoming a more and more of a problem nowadays, because one satellite has been just abandoned, and if it's hit by a rock or by a tiny particle, it becomes millions of shattered pieces. It basically threatens all others that are still operating.
That's the risk of that chain reaction in space.
Yeah.
One satellite gets blown into a million pieces, which hits 5 more satellites, and they blow up into a million pieces, and then suddenly you've just got all your satellites running into debris and destroying.
So, at the moment, it's on the edge between theory, but it can become real very quickly.
Do you know, with satellites, do they generally travel the same way around the Earth? Like, do they all kind of head the same way around, or are they all? Because I imagine, because thinking about that, if there's so many up there and you're trying to stop them from running into one another, you think it would be easy. It's like, okay, everyone drive on this side of the road. Like, all these satellites go in this direction, so then we're not going to have like head-on smashes with them coming at each other or sort of coming across one another. But
now, well, imagine, a satellite, even if it's the size of a school bus compared to the size of the Earth, it's really nothing.
Yeah.
But from a purely operational point of view, so you have the Earth, right? The ball. If they fly from north to south, as the Earth rotates, you can capture everything from the north to the south pole, and everything you can capture, right?
Yep.
But if they fly like this, even at an angle, you are not able to capture the
poles,
the extremities.
Yeah.
So it actually depends on what are they designed for.
Yeah.
Most satellites that are for either civilian or military purposes, they fly from north to south.
So they can monitor the entire
planet. So they can monitor anything. But there are satellites designed specifically, like there are private companies focused on specific areas around the equator, obviously to a wide range, usually about 45 degrees, even more. And they've decided to fly in this way. So we have both.
I saw a couple of years ago, one night here, I saw a link, what they call a chain of the Starlink satellites going up. And I was told that when they're going up, or when they've been released and being put into orbit, is when you can see them, because they're oriented in a way so that they're solar panels. I don't know what they are, but you can actually see them. So, and we could see this chain of satellites going. Yeah. But then you can't see them again after that. Once they're sort of in position, you don't see that long line of them every night going around anymore. So they. I wonder what they're doing, because they I guess are actually just being distributed all around the globe so that they can provide internet service anywhere, or do they? I wonder, or do they run, like you're saying, around the equator, and they're able to reach where they need to go from there?
That's a bit outside of my field, so I don't know to answer that, because it's a very different application, providing internet versus taking images. So
it's interesting stuff though. I've often wondered about them. Years ago when I was at university, I remember even then the topic you were talking about before, the idea of space junk, it was one that we were starting to think about, because there's just so much up there. And I don't know if there's work being done on it, but I wonder if there is a way to go up there and sort of start to capture space junk, send up a big net or something that flies around and just sucks up, spits. It's a bit elastic, bits and pieces of blown up satellites just ran into it and attached to it, but at least you're kind of collecting it all.
I know there are companies that are designing solutions to monitor space junk, so you can begin to monitor but I'm not aware of any solutions to actually clean it up yet.
Yeah, or we needed to send up a big ball, just a big ball with a bit of gravity and mass, just to suck all that stuff towards it.
I mean, realistically, space is a very exciting. It sounds very exciting. It's an exciting endeavor. Sending satellites into space, flying into space. Let's do this new startup to clean this and that. And that's cool, but the reality is, as you cross from I have a passion for space to working into solving problems, you see that it's a completely different story. It's much harder.
Yeah.
So enthusiasm and passion is one thing. But, we have ideas to clean this stuff, but the reality is we cannot clean the oceans of plastic at the moment. So how much more to clean the space of junk?
It's probably got to make money. It's got to get to the point where people are saying, hey, this is costing us lots of money. We're losing lots of satellites. We need to fix this. And then
it's probably going to be some years.
Yeah.
Yeah, I'm not skeptical in the sense of I know there's a lot of enthusiasm, but when crossing from that enthusiasm to the real hard reality, that's why it takes years to build a satellite. That's why, Hubble took 20 years, 15 years. James Webb took 10 years. It's really hard science.
Oh, yeah, that is, because that has to be almost, in some respects, a pinnacle of science, because you are trying to build instruments on the edge of our capability with with the most advanced technology and processes we've got, and battling that against trying to make it weigh as little as possible. It's not like building a telescope here on Earth. Go for it. Make it be incredibly advanced. Doesn't matter how much it weighs. It's going to sit on the Earth. But if you've got to put it into space, suddenly you've got these constraints. Like, how do we make it awesome, but also make it lightweight? And balancing that. And
you have all sorts of... So it's something like, for example, like James Webb. It's an extraordinary feat of technology, and it's mind-blowing. So when it comes to cleaning space junk, and it's not that easy.
Yeah.
I can say I was very blessed to have as my mentor the director from NASA he led the team that built Hubble Space Telescope. So for some years I was kind of his I was learning from him the social part of managing technical teams. And he taught me some amazing things, because Hubble, for example, it was a masterpiece of technology, built in the 1980s, 1990s. Actually, 1980s. It was launched in 1990. It took 15 years and $2 billion to build and to launch, and they launched it and it failed. So, and then when they started investigating why did Hubble fail, they found there was a technical problem with one of the mirrors, and it couldn't focus properly. And the investigation committee asked the question, or how is it possible that you spent 15 years, almost $2 billion to build this, you have the best minds working on it, you had Nobel Prize winners, you had PhDs, and they made a technical error that only an amateur could make, and this satellite didn't work. How is it possible? And that's when the investigations kind of began to unfold the fact that there is a social risk associated with high technical projects. No matter how smart the people are, no matter how brilliant they are, no matter the degrees, and if you take good people and you place them in a toxic environment, in a bad environment, eventually it can lead to failure. So the root cause of even NASA and highly technical projects, the social risk needs to be managed properly.
Yeah, it's a really interesting idea. You do. With people, or any environment, if people are having personality clashes, well, they stop communicating. So, you know, if someone might have seen a problem, but they're like, I'm not going to tell him it's his problem. He can sort it out.
That's exactly what happened to Hubble.
Was it?
Yeah.
Yeah.
So the context was so toxic and so psychologically violent that engineers discovered the problem, but it was small enough to be rationalized away and to be just swept under, but big enough to destroy the satellite.
With Hubble, though, were they able to recover from that? And while it was in space?
Yes, another $600 million. They sent astronauts into space and they flew the space shuttle and they fixed it. They put a pair of glasses, like
Wow. Contact lenses.
yeah, that's how they did it, and they fixed it.
So that's amazing. That actually does amaze me about satellites and space technology and like the rovers and things on Mars when they recognize, we've got some problem, but we think we can get around it. We can work around, with what we are capable to manage remotely. We think we can overcome this. It's pretty amazing.
Yeah, well, you can't go to Mars yet, so.
No, but hey, we're getting close. Starship launched 2 days ago. Went up.
Almost.
Well, I'm not sure what the plan for the test was, but I think the key thing was they got the Starship off the ground with the Falcon Heavy underneath it, got up and out there. I'm sure they were probably going to try to separate it and then re-land them. But I think the key thing for them was, hey, it didn't blow up on takeoff. We actually got the thing up and it flew. And I'm not even sure if maybe it did actually have a failure upon trying to separate. That may have been where the problem was. But still,
yeah, but it's part of the journey, so it's
yeah.
Yeah.
I saw a whole heap of people on Twitter just flaming Elon, loser, blah blah blah. I don't think Elon gives a fuck. I think he's like, this is just part of the process, man. We're the first people to do this. Of course, we're going to have problems.
Yeah, I mean, I'm sure those who criticize they cannot even send probably a kite into the air, but
exactly.
How much more? Yeah.
What did amaze me was that not far from Ground Zero there was a camera crew, a news crew or something. I don't know who it was, but they had a car and they had a little arm on it with a little GoPro or whatever it might be. And I'm not sure how far it was from the bottom of the rocket. I want to say maybe it was 100 meters. Maybe it was more, maybe it was less, but yeah, it wasn't far away, but it wasn't like right underneath the rocket. Anyhow, when it took off, this the massive smoke and air and whatever just being blown out from it, it was just picking up, I think, rocks from the ground and throwing them around. Like one of them hit this camera and the camera just goes, sort of spins off and rolling around the ground. And I imagine their truck got buffeted by it. I just don't think, unless you're there and see it, that you can imagine how much power that rocket system has. It's just insane.
Yeah, I did see 2 launches more than 10 years ago from NASA in Florida. But obviously different rockets, but the amount of power, you have to be there.
Yeah, you just have to be. The sound would be phenomenal of a rocket launch. Again, I can't imagine it. I can't imagine what it would be like unless you've heard it. And I saw some footage from, I don't know if it was a SpaceX flight or if it was someone else recently, and they had a camera on the rocket looking back at the Earth.
Oh yeah, all of them usually have that nowadays. Yeah,
and just in real time, the acceleration of those things. Again, don't think you can appreciate the acceleration unless you're either sitting on it or you're there and watching it. But from that view, you could just see how rapidly the Earth just became tiny and disappeared. And it was like in a matter of seconds, in 30 seconds, you're like, geez, that thing's going so fast. Yeah. So the satellites that are up there, they do have power supplies for maneuverability, do they?
Yep.
What? Battery power, is it?
Battery, fuel, solar, all sorts of things.
Really?
Yeah.
I had no idea that they would put fuel into them.
And you can lower them. You can make them fly higher, up to obviously some intervals. Even some military ones, they fly at a specific altitude, but if you want to increase the resolution, you lower them.
Drop them down. Yeah.
Drop them down, take the picture.
And put them back up. Well, I had no idea. I thought they were up there and unpowered. I thought they were just balanced by gravity against the centrifugal force, or whatever, just holding them there. They had no ability to move.
Well, yes, but it's both. So they don't. You don't constantly burn the fuel.
Yeah.
But there's times when you need to burn the fuel.
Did you see that one that came in about 3 or 4 years ago at summertime? I think it was a Russian satellite that came across New Zealand and burnt up on re-entry. We were really lucky. We got to see it. We were just up north at a friend's house on the coast, and I don't know. It was summertime. It was in the evening, so it might have been 8 o'clock in the evening. And we just looked up and went, wow. And we thought, wow, that's like a shooting star. And then you thought, my God, that's the biggest shooting star I've ever seen. And then you realized this was something else. Because this thing just went, and it was just continuously burning across the sky and just went from the north all the way across us, all the way down towards Auckland and beyond and beyond.
No, I didn't see that.
Yeah, it was awesome. I wish that somehow we'd had a camera to film it. It was really quite amazing to watch. But again, that's something that's hard for me to comprehend, is that things burn up on the way in. Because you think, oh well, there's hardly anything up there. There's no air particles up there. There's bugger all space. It's a vacuum. Well, then no, but you start to hit those few air particles, they warm you up. It's just, again, it's difficult to imagine. I kind of imagine you just fall in, no problems. But I know that on the space shuttle, that's where they had problems because they had, what do they call them?
With Columbia.
Yeah, with the ablative tiles, which would take up enough heat and then start to sort of deteriorate. But they had to get that balance just right. If they were coming in too slow or something, or too fast, they'd overheat them, they'd cook through, and they could cause problems with the. Yeah,
that's why Columbia exploded in re-entry.
That was why, was it?
So the heat shield under the rocket, under the space shuttle, is designed to withstand the atmosphere and the burning through. But in the case of Columbia, I think one of the tiles either fell off or wasn't properly was not put in place, and when the shuttle went through, it exploded on re-entry.
Yeah. Okay. There's a company, I can't think of who it is. I saw them on YouTube the other day. They're building a reusable capsule. So it'll sit on top. Have I got this right? Yeah, I think it sits on top of a main rocket, which will take it into orbit at some height, and then this capsule has its own rocket propulsion to take it further to wherever it needs to go. But this is a reusable component, and so it's sort of like a round pyramid, sort of a cone-shaped thing. But what they're doing, when it comes back in, it comes in butt first, comes in bum first. The round part and the pointy part is still pointing out at space. Yeah. Because it's got to reland, so it needs to be able to maneuver, so it needs to fire its jets again when it relands. Instead of having like ablative tiles and heat-resistant material on the bottom, they get better performance from the fuel in the rocket if it's been preheated. So they've designed the bottom of it such that when it comes in to re-enter, they start to pump the cryogenic cold fuel into the base of it, which gets heated up by the friction of re-entry. And then when they want, and that keeps it balanced, stops the material from melting. And then when it's time to fire their engines to position themselves for re-entry, the fuel's warm and they're ready to go.
Okay.
It's a really clever, efficient use of the...
To warm up the fuel.
They've sort of taken a problem and turned it into an advantage for them.
Yeah.
So what sort of work are you doing now? Are you doing like GIS work or space observation work or?
No, so recently I shifted. I'm still in the space industry, but I shifted towards strategy development. So basically, what I do, I develop strategies for Earth observation and geospatial. And when I say strategies, I'm not talking about the strategies that you are used to in the 70s. I'm focusing on today's reality, which is very different context, very different environment that back in the 70s. Nowadays, you as an organization, you can't have a strategy more than 2 to 3 years in advance. You can't, because you don't know what's going to happen,
In terms of technology changes and geopolitics and whatever.
All of this, you can't predict more than, let's say, 3 years.
Yeah.
So basically what I'm doing is I'm just enabling countries, governments, private companies to profit from Earth observation and geospatial. Because you have a wealth of data, you have a wealth of technologies, and I'm just basically developing disruptive strategies that are very quick to implement, quick to deploy, quick to produce results, and to get a return for for the customer.
So are you looking at working with people who will, like you said before, with the companies who use they use the Copernicus data, they take that data and then they develop it into a service for end users? Or are you looking at working more with the end users themselves to access that data and do something with them?
No, so I've taken a very different approach to strategy, in the sense that when it comes to building a strategy, because it's the easiest way, what normally gets done is, let's focus on the use case. What do you want to do? Do you want to do disaster monitoring? Do you want to do agriculture? Do you want to do this or that? So that's one way of doing things, but I have not taken that approach. So my approach is at the foundational level, in the sense of I'm looking horizontally at the widest pool of users, and then I put the strategy to serve the biggest pool
Group
of users. So let's say, for example, you are a government agency, right? So as a government agency, usually you have many departments. The traditional way of approaching strategy would be, let's focus on this department and do this. But my answer is no, I'll take it to a more foundational level and say, let's look at all of the stakeholders.
What's the opportunity that may apply to all of them?
So what is this trying to do? What is this trying to do? And what are each of your customers or your stakeholders trying to achieve? So the conversation is two ways. You talk to them, trying to see what is their goal, their vision, ambitions, hopes, what they are really trying to do from a practical point of view. So I don't want to know the philosophical hopes, I want to know the practical realities. And then once you also show them what are the latest capabilities with Earth observations, because when you begin to show them, this is what you can do, this is what's possible, ideas begin to pop into their heads. So once you have all of stakeholders mapped out, you will see that there's a common ground where most of them and their needs, requirements kind of meet. And then using the Earth observation, the geospatial technical knowledge, you design a solution to meet that joint pool of needs and requirements. So in this way, you can actually make not just one use case happy, but you can make a lot of stakeholders happy.
Yeah.
So that's my approach to strategy. And I have 5, I wouldn't call them principles, but 5 ideas I usually follow when it comes to strategy development. Number 1 is the strategy is the how. So it's not about philosophical concepts, fluffy words. We improve customer experience, we improve customer satisfaction. That means nothing. Whether you're using Earth observation or selling sugar drinks, it is the same words, So that doesn't bring any.
What's the concrete thing that we can do here?
But usually a strategy is you are in a situation that looks the way it looks, and you can measure it or you can understand it. You operate within a context because things do not work across contexts. So I cannot take some ideas from here and apply it in Asia, or because it might not work.
Yeah.
So you have to be very aware of the environment you're in. then okay, we want to achieve this in the next 3 years, we want to be there. The strategy is the practical way of how you get there. So that's the first thing. The second thing is that it is I'm oftentimes asked at conferences, how do you get stakeholder buy-in, how do you convince them? And so I never have to do that. And I really never have to do that, because a strategy is not about you. It's not about you, it's about them.
Yeah.
So if you come into this conversation with the idea, I want to do this, let me try to see how I convince you.
Then you need to get the buy-in.
It's never going to work. It's going to be very hard to work.
But if you come in and say, what do you want?
Yeah, and if you remove yourself from the conversation and you truly ask, what do you want? And then think how you can serve them, it's easy.
You've got the buy-in already.
Yeah, because they tell you what you want and you just do your best to help, and it's easy.
Yeah.
And then the third thing is build something within the means you have available. And oftentimes there's a stumbling block saying, oh, I want to achieve great things, but it's too hard. I want to run a big program, but we don't have the finances, and I want to do this great strategy, and then nothing is done. But my theory is, well, if you can't build the big thing, why don't you build the small thing? You want to build the big program, but you don't build the small one.
Yeah.
You want to build a big strategy using thousands of dollars, and if you don't have them, you stop. Why don't you just use a piece of paper and a pen and start drafting something?
Yeah.
So whatever you have available, use that and build something. I've worked for central government. The budget was extremely tiny. I developed a strategy within that means. After 5 years, 6 years, that product with only a few thousands of dollars, it's still working.
Yeah.
So build something within the means that you have. It's not an excuse not to do it, The fourth one is deliver the most simple, user-friendly products. The more simple it is, the easier to use, the happier the stakeholders will be. That's why technical people are not the best of designing strategies, because they want to build cool toys, but users don't necessarily want them.
They want simplicity. They want to get a job done easily, quickly.
Like if I use my smartphone, I want to press a button, call my parents. I don't want to learn code to use some, I don't have to write code to be able to make a phone call.
Exactly.
And it's the same users just want to get their job done, and the most simple it is, the best it is.
Yeah.
And number 5 is, and this is my favorite, I've learned this from Silicon Valley, is doing always comes before knowing. So a strategy is like a scientific theory, and it comes to, you plan it out and you say, this is the roadmap. But then it comes a point, usually very early on, where you get blocked and you don't know what to do. Like, what do I do now? Managers or customers say, this can't be done, we don't have this, we don't have that. You get stuck. And when you simply don't know what to do, you just do the next thing.
Yeah.
Because you just do the next thing. Whatever comes to mind, whatever is, legally moral, you just do it and see what happens.
That's right.
Because how many times I came to this roadblock and say, this can't be done, it's not possible. And I said to the customer or the one sponsoring the program, I said, can you just try? Just try. Oh, but we will not get approval. We will not. The context is, I said, that's fine. But take the step and see what happens. Almost always, it works.
You progress, you go ahead. Yeah.
I think I have this, when I speak at conferences, I show this picture of somebody's drawing an airplane, in the ancient past, putting wings on a piece of paper and drawing the wings and the wheels and all that, like the first model airplanes. And then the next one is this guy trying to fly one of these designs. Which of the two do you think knows more about flying? The one who keeps drawing and thinking and thinking?
Or the guy who's crashed?
Or the one who's put his legs and his body on that thing and see,
Yeah.
if it doesn't work, he learns extremely fast.
It's a really good. Yeah, the fifth one's a really good idea that the knowing comes.
Yeah.
Comes before because
the doing comes before understanding.
Yeah, before the knowing. That's right. You think about it, you got a theory. Yeah, I think this will work. You go out and try it. Oh, okay, I've learned something now. That doesn't work.
Yes.
Yeah. It reminds me of, I think it was Mike Tyson whose quote about boxing is, everyone's got a plan until they get punched in the face. And then everything changes. You're like, now what am I going to do? Well, you're learning.
Yeah.
Yeah. Yeah, they're really good points, really valid points. So much, I think, I work in software. So much of that is, what has been the learning for me, the big learning about building software after many years is ask the users what they want and make it as simple as you can.
Yeah.
You know, because I've seen a lot of business owners, you know, when they want to build a website for their company, they come to you and they say, hey, we want to build this great thing. We want to do this and that on our website. It'd be awesome. And everyone will come to us. You kind of got to break it to them. It's like, well, why will they come to you? Well, because this will be awesome. It's like, yeah, there's a lot of other things just like that out there that are already using. Why is yours better? Well, I don't really know. Yeah, it's probably not really going to work. You know, what you want to do is, you know, what is the thing that your customers do with you today? Is there a way that you can do it online and you can make that better for them? Can you make it faster for them? Can you make it cheaper for them? Can you make it easier for them? If you can do that, and if it's just one thing, start with one little thing that they do today and maybe they have to call you or they have to fill out a form.
Yep.
If you can take that away and make it easier for them so they can now do it at 8 o'clock at night when you're not open, that will be successful for you. They'll use that. And then if you can think of the second thing that they can do and you can put that next to it, now these customers are going to really start loving you and they'll start coming online and you'll decrease your costs and that.
Yeah.
But if you go out and build this big majestic thing and open the doors and say, here it is, people are just going to go, wow, it's a bit complicated, man. I don't need all that rubbish over there. That thing's okay, but yeah. Ask the users. Make it easy.
Yeah, it's not like in the movies when build it and they will come. Sometimes you build it and they don't come.
Lots of people have built it and it didn't come. That happens a lot. Yeah. And again, it's like you said, if you can't do the big thing, do the small thing. Start with something small. Like do some little thing that will deliver some value. Like if we can identify that, if we just, we want to get over there, great. You know, but if we can build this thing here and that would be valuable to these people, well, we'll probably get a tick from all those people. They'll like it.
This is probably I think the best career advice I got. I mean, it's been throughout my life as a theme. If you are not, actually, it's also what Jesus taught in the Bible. If you're not faithful in the little things, who can entrust you with the big things?
Yeah.
So in your career, say, I want to lead a team. I want to be a leader. I want to be this and that. Yes. But are you able to send an email if I ask you to do that?
Yeah.
Oh no, I'm too important for that. No. Yeah. So if you're not capable in delivering a little thing, how can I give you more?
Yeah.
You know, if let's say if you're in a position to maybe build a strategy or even to bring, let's say, Earth observation in your organization. You know, we heard of this cool thing. We don't know what it is. We don't have budget. Can you help? And you know, you want to do. We can build this platform that costs hundreds of thousands. We can, and say, well, I'm not giving you that. And then you give up. But no, can you deliver? Can you bring me a free satellite image that I can see the value of it? You know, because sometimes the strategy can just be that kind of simple. I'm gonna take one free satellite image every month. Or maybe once a year, and I'm going to draw the extent of the forest in my area, and that's it.
That's all we need.
But even that, you know, can you deliver that? If you can't give the platform and the AI and the machine learning, can you download the satellite image once a year and draw a map and give me the output?
And compare it to another one, yeah.
So is that the practical small things that added one after another that leads to
Value.
to value.
Yeah.
For example, with the European Space Agency, I remember 10 years ago, less than 10% of the satellite images captured have been downloaded. I'm not saying used, I'm saying downloaded. So how much of that 10% is actually used? I remember downloading so much and never even archiving them.
Yeah.
You know, you download and then you just delete.
Yeah.
So
maybe 1% has ever been used.
Yeah.
Yeah.
But that thing is enough to create value for what you need.
Yeah.
So I like very simple ways of doing things. You know, it's...
Yeah, I've got to admit, I'm the same. I think it's like it's one of those agile ideas too. It's like an MVP. Build the minimum viable product. Do the smallest thing we can do today. What can we achieve today that would be valuable? Then tomorrow we can add to it.
When I went, I was in Silicon Valley some 7 years ago, and they taught us a really cool thing about designing apps. So, you know, rather than designing an app, programming an app, putting it on the phone, going around asking users, what do you think of this?
Yeah.
The approach was different. They said, take Post-its, like stickers, draw the app on the stickers, put the stickers on the phone, and go to the users and say, what do you think of this?
Yeah.
And the user said, okay, I'm going to press this. And then this shows up. I don't like this. Nah, it's not going to work.
Yeah.
Much more efficient.
Oh, and the feedback, the information
How
you've
much
got.
is a Post-it pack?
Yeah, that's right. It's cost you nothing. And now you've done some of your knowing. You've got some of your knowing. You're learning.
Yeah.
You know, like you had an idea. Now you've tested it, paper prototyped it really quickly. And suddenly you've jumped way ahead. You didn't spend any money on building code and putting something out there that people don't like.
Yeah.
Yeah.
So I've done my strategies. You can fit them on a piece of paper on one page. So if you can't fit them on one page, it's probably not good.
Yeah. Yeah, I like the idea too, what you talk about now, like strategies for today, needing to have that relatively short-term focus.
Yeah.
Because right now, you can just see it now. And I'm talking the last 2 weeks, the explosion of AI tools that have come out and are available now for typing in, this is what I want my website to be. Bring. It just pumps it out, or whatever it might be. You know, I remember I was on the podcast, I was talking to someone 3 months ago and saying to them, look, it can't be far before you'll be able to just talk to an AI and it'll give you a song. So just this week, Universal Music Group have just made this guy pull down this track that he created with AI, which was of Drake and The Weeknd, and he just got AI and basically said to the AI, give me a song where the voice sounds like Drake and the backup vocals sound like The Weeknd, and it built this song. And apparently, I didn't hear it because it got pulled down up by the time I'd heard about it. Apparently it was a good song. It had 600,000 downloads on Spotify, and like it was a popular song. It was just AI. You're going to be able to, in the next month, go to some AI somewhere and go, give me a new Pink Floyd album, or give me a new Beatles album, or whatever it is, whoever you love. And it's just going to go and spit it out. And it'll be all these songs that'll sound just like the people in the band singing. It'll sound just like them, but it'll be completely new, never been heard before. And then it's going to be a movie. You'll just sit down on Friday night, instead of going to Netflix, scrolling through films, you'll just say, give me a movie that's a bit like Dune, space, noir, kind of freaky, some cool aliens, lots of explosions. And it's just going to go and start.
Oh, well, actually, Netflix has already done a similar thing in the sense that they've used AI to learn what are the most watched movies. And then they designed a new series based on that information.
Yeah.
So all the favorite things that people watch, and it was massively successful.
Was it? Yeah. That makes sense. That does make sense.
So it's learning from experience from the past and then designing something to exactly meet the preferences.
Yeah. I can see the personalisation that AI will bring to services will be massive. And the example is there's this particular like sort of niche of I don't know what you call it, chill out, trip hop music from about 2004 to 2008. There's a period there. I just love that stuff. It's the stuff I like to put in the background while I'm working. But it's a limited, finite resource. You know, the music that was made by bands in that period of time, you're not making that anymore. Things have changed.
Okay.
But to be able to go to Spotify or Pandora or whatever the service is and just say, can you just give me a continuous stream of stuff that sounds like, you know, 07 and this guy and that guy and that guy, and it'll go, yeah, sure, we'll just make it up for you. And all day you just be going, I love this stuff. This is exactly what I want. But it's all new. That's you know, I think that's going to be an amazing service. It'll be like, here's your Spotify service. Oh, do you want Spotify personalized where you can auto create whatever you like? Yeah. People will pay the extra $12 a month for that.
Okay.
I think that'll happen. But I'm looking forward to the sit down in front of the TV on a Friday night. Just say, what do we want to watch? Oh, a horror film that's full of ducks. Okay, let's go. And then the TV will start and characters will turn up and, you know, because it's already, that stuff is already happening. Text to video is already happening. Once it becomes a little more powerful and commercially available, it'll just become a Netflix service. Instead of $14 a month, it'll be $28 a month, but you get to do your own creation. And if it's good, and I imagine that pretty quickly it'll be good, everyone will want that service. You know, if you don't have that on your Netflix, and you'll feel like, oh, I can only watch the films that are actual real films created by real humans. I can't get any of this cool stuff. Yeah.
We'll see.
Yeah, I think so. Dragos, thank you very much.
No,
for
thank
coming
you.
in. It's been really interesting talking to you.
Thanks for having me.
Oh, that's all right. We should do it again sometime. Yeah, cool.
Done,
Done, man. Yeah.
Wow, it's
Well,
1.5 hours.
Yeah.